Hello everyone, welcome back. Today is going to be our quiz review. Rather than making a set of notes or something to go with the quiz review today, I'm just going to work straight off of the MyOpenMath problems that we see over here. So that way we can talk about some of the little nuances that happen in MyOpenMath, like with picking little things out of the instructions or entering in answers and things like that. So I'm hoping that this video will kind of clear up some of those things if you were struggling with inputting answers or catching little things out of the instructions. All right. So here we go. We're taking a look here at the first question on our review. We have a teacher who wishes to distribute 50 identical pieces of candy among 4 students based on how many pages of a book they read last month. All right. And we're going to use Hamilton's method. Make sure that when you're reading the directions for these problems that you look for the method in each question. So I always get a few students that, instead of using Hamilton's method, they might try and do this with Jefferson's and vice versa. So just make sure you know what method you're using for each problem. All right, so we have a table here. We've got Miguel, Josh, DeAndre, and Andre, and these are the number of pages that they read, so we're going to use this for our apportionment. Now, in MyOpenMath, I gave you a link to a file that has a bunch of tables in it. So these tables could be useful for like doing your work with the apportionment tables or with the apportionment problems. And I left the headers blank so that way you can just label the columns however you like when you do your problem. Some of you probably set up in different ways, so I tried to leave it as open as I could. The state, the population, and the quota will always be 3 things that you calculate no matter what. So I went ahead and filled those in for you. The other thing to notice on the second page of that file is that on the back page you'll notice stuff that says like geometric mean and HH final. That is a table that is specific for the last apportionment method that we're going to learn, which is the Huntington-Hill method. So save those for next week. All right, and we can just use the ones on the front here for any Hamilton or Jefferson or Webster method problem that we might run into. Okay, so I'm going to take the information from this table and I'm going to transfer it over here to my apportionment tables. All right, so I've got the information transferred over. So what I'm going to do first here is I'm going to work on finding the divisor for this problem. So I'm going to take all of these populations here, I'm going to add them together and get a total. All right, so you can see that I have added my 4 populations together. So this is the total population, or actually the total number of pages that the students read. And remember, we are apportioning 50 pieces of candy among these 4 students. So to get my divisor, I'm going to take the 1,970 and divide by 50. So our divisor is going to be 39.4. And I'm just going to write that up here above the table so that I can use it for later. Now I'm going to use my divisor to help me find the quotas. So I'm going to take each individual population listed here and I'm going to divide it by 39.4. All right, so I went through and I divided each of my individual populations by 39.4, and I got these numbers over here. These are the quotas, which I've already transferred over to my table here. Notice that I rounded all of my quotas to 4 decimal places to make sure that I get that correct. If you recall, in the problem, they want you to give at least 4 decimal places as appropriate. Okay, so make sure that if you see a rounding instruction in a problem, that you abide by that rounding instruction. So if it says 4 decimal places and you only round to 3, it will count it wrong. Okay, so to continue on with Hamilton's method here, we're going to get an initial apportionment. Right, and we're going to do that by ignoring all of the decimal portions and taking the whole number parts of the quotas. So 9, 14, 8, and 18. And then we will add those up and see if we have apportioned enough. So initially we have apportioned 49 pieces of candy based on what I see here. So there is 1 bonus piece of candy that needs to be awarded. That bonus piece of candy will be awarded to the reader who had the highest decimal portion in the quotas. So if I go back to the quotas, we see 18.5. The 0.5 is the largest decimal portion after the whole number. So the 18 will get the bonus candy, and go from 18 to 19. The rest will stay the same, and this becomes our final apportionment, which will total up to 50, which is how many pieces of candy we needed to apportion. So now that I have finished the apportionment problem, I should be able to answer all of the questions that are asked for here in my open math. The first question asks for the divisor, which we found first, which was 39.4. It does say to round to 4 decimal places, but since this one only goes to 1, you could put in 4000 if you want, but I think 39.4 would work just fine. Find the quota for Josh. So Josh has a quota of 14.0863. So this one I need to be careful with my rounding. And then it says find the initial apportionment for Josh. So the initial apportionment, right, is this column. Before we awarded any of the bonus candies, we want to make sure that we pull the 14 that he has from the initial column. Now, if we had awarded Josh an extra piece of candy or a bonus piece of candy, his final would have been 15. A lot of students tend to put in the final even though the question asks for the initial. So make sure that you understand the difference between the initial apportionment and the final apportionment when it comes to Hamilton's method. All right, for the next problem, we have a college that offers tutoring in math, English, chemistry, and biology. The number of students enrolled in each subject is listed below. If the college can only afford to hire 14 tutors, determine how many tutors should be assigned to each subject using Jefferson's method. All right, so this one's not using Hamilton's, it is using Jefferson's. And when I look at the table where they want me to enter in answers, they want the actual number of tutors to assign. So that's going to be the equivalent of the final apportionment when we're done with the problem. Also, they want us to enter in the modified divisor that we use. So remember, with Jefferson's method, there is a chance that we might need to modify the divisor to get the correct final apportionment. All right, so let's go through and do this. The first thing we're going to do is we're going to add up the populations to get a total population here. All right, so you'll see here on my calculator, I've got my four populations. They are added up. We got a grand total of 770. So I'll write that down over here. So we got 770 for our total population. And then to figure out the divisor, I went ahead and divided that by the number of tutors. So if I take 770 divided by 14, we get 55. So this 55 serves as our divisor. So now to figure out my quotas, I'm going to go through and divide each individual population by the divisor. All right, I have divided each one. So these become my quotas over here, which I have already put into my table. And now I'm going to get what's called an initial apportionment. All right, so Jefferson said to go ahead and ignore the decimal parts and take the whole number parts of the quotas. So we have 5, 4, 2, and 1. And when I add those together, I get 12. So that is not enough. We needed to apportion 14 tutors, but unlike Hamilton, rather than awarding bonus tutors to the highest decimal portions, we're going to modify the divisor. So I'm going to change the divisor down to 48. And I'm going to redo my quotas. And my initial apportionment here will change. Okay, so I have went through and I redivided all of my populations by my modified divisor, which is 48, and I got my quotas, which I have already put into my table here, and I'm going to go ahead and chop off those decimal portions again to get my initial apportionment. So we got 6, 5, 2, and 1. That should be a 5. There we go, and then I will add those up to make sure that I have apportioned enough. So 6 and 5, 2 and 1, so that is 14. So that is enough, so this divisor would work, and this becomes my final apportionment. Right, so I'm going to go back to my open math and make sure that I enter in my answers here. So I'm going to go here to the apportionment that I got with my modified divisor, and I'm going to enter in 6, 5, 2, and 1. and then the divisor that I used was 48. Now this answer can be different. It doesn't have to be 48 here. Some of you might have come up with a different divisor that worked. 48 is not the only one that will work. All right, and remember this 48, I just chose that at random, so you might choose a divisor and it might not work the first time, so you might have to try another one. Okay, so it is a trial and error type method. There's no way around it. Okay. All right, next question here for problem 3. It's a very similar problem to the ones that we were talking about before where we have to apportion tutors, but this time we're going to use Webster's method to do it. All right, and you'll notice that there is a column for the initial allocation and the tutors to assign. Okay, so the tutors to assign will be the final apportionment when we're all done with Webster's method, and the initial allocation will come after we do the allocation with the initial divisor before we modify. All right, and I'll demonstrate that when we get to it. All right, so I've already got my population fields filled in over here on my table, and I'm going to go through and calculate my divisor. Okay, so you'll see that I added up my 4 populations here. I got 830 total students, and I divided that by the 19 tutors that we need to apportion. So I got an initial divisor, or an original divisor, of 43.68421. So I'm going to write that down. There we go, and I rounded to 4 decimal places, and now I'm going to go through and calculate my quotas. So I'm going to take the individual populations and divide them by that divisor. All right, so I got my individual populations divided, and I got my quotas over here. So I went ahead and filled those in on my table, and now I'm going to get my initial apportionment here. And remember, what Webster said to do was not to ignore the decimal parts this time, but rather use them to round. Okay, so 8.58 would round up to 9, 6.2952 would round to 6, 2.5181 would round up to 3, and 1.6 would round up to 2. And then we would add those together. So 9 and 6 is 15, 15 and 5 gives us 20, which is too many. And now we can actually fill in the first part of our table. This is the initial allocation that they want for this first column. Okay, so I'm going to go ahead and fill in those numbers. Okay. And then what we need to find is the final number of tutors to assign. Now you'll notice down here I have already entered in the modified divisor that I'm going to choose next, and it is a weird one, 44.1. And what you guys don't see off camera is all of the different divisors that I tried to try and figure out this problem. It's the ugly part of using Webster's or Jefferson's. I actually had to try 4 different divisors before I finally found that 44.1 worked. So I just kept on going up and down, trying to narrow where that divisor would work at, and I finally found that 44.1 would work. So I entered it in to MyOpenMath and just clicked enter to see if it would accept it as correct, so that I know that my 44.1 is good to go. And then I'm going to go back and use that 44.1 to recalculate my quotas and get a new apportionment. So I'm going to set up the next part of my table here. And this will be the final, because I know it's going to work. All right, so quota, final, and we're using a divisor of 44.1 to recalculate our quotas. All right, so I have my quotas recalculated. Now I'm going to use rounding to get my next apportionment. So 8.5 will round up to 9, 6.2 will stay at 6, 2.4943 will stay at 2, and 1.58 will round up to 2. So 9 plus 6 is 15, 17, 19, which is the number that we wanted. So the 19 becomes, or the apportionment here in this column becomes my final apportionment, and this becomes the divisor that I'm going to use. I'm going to go back to MyOpenMath and enter in the number of tutors. So now we're going to assign 9, 6, oops, 2 and 2. There we go. right, so this problem right here, I'm not going to work through this one in detail, but I will just note that you are doing all three of the apportionment methods. So you'll run through a Hamilton, then you'll run through a Jefferson, and then you'll run through a Webster, and you'll enter in the final apportionments for each in these columns. Okay, so it doesn't say final apportionment up here, but that is what they want. So when they do the Hamilton apportionment for this column, they want the final apportionment for each of the methods. All right, now here in the next problem, what they have done here is they went ahead and they apportioned these 38 seats in Congress using Hamilton's method, and they give you that apportionment right here. All right, now I'm not going to work through the details of the apportionment for this one because I've already done an example of Hamilton's method, but down here they're telling you that they decide to expand Congress by one additional seat, and they want you to do a reapportionment with the same populations and the same states, but with 39 seats in Congress rather than 38. And then they want you to compare those apportionments to what we originally got when we had 38 seats. All right, so this is a setup for what's called the Alabama paradox. All right, now the Alabama paradox doesn't necessarily have to happen here. We could reapportion with 39 seats and everything works out just fine, in which case you would select none of the above. But if someone's apportionment goes down as a result of increasing the number of seats, that is a demonstration of the Alabama paradox. So you're looking for one of these to go down. If none of them go down and they all go up, or one of them goes up and then the rest stay the same, that's fine. Then you would select none of the above. None of the paradoxes occurred. Okay. And then finally here in the last problem, all right, we have a country with 4 states. They are apportioning 30 seats, and they did that apportionment here for you. And then what happens is after the apportionment, they add a new state. So you can see them adding the new state population down here at the bottom of the table. So you'll label that state E, and they tell you the population and that they are going to expand the Congress by 3. So they added a new state and added 3 new seats. So you should recognize this situation as a setup for the new states paradox. All right. You'll rerun the apportionment with the new parameters, so the new state and the 3 additional Congress seats, and see what you get. And you'll do that using Hamilton's method. Once you get your apportionment, compare your apportionment to the original apportionment. If you notice that state A, B, C, or D lose one of their members or one of their seats, then the new states paradox has occurred. But if they didn't, if they went up or they stayed the same, then none of the above happened. None of the paradoxes happened. Okay, so this is just an exercise in trying to identify which paradoxes exist and when they occur. All right, guys, that's it for the review for today. Hopefully you found this helpful. If not, make sure you ask some questions in the Zoom chat. I'm more than happy to help you out. All right, guys, have a great day.